This is the solution to group problem solution number 17 for class 17. So this is a problem of a water jet coming in from the left at a uniform velocity of 3 meters per second, and the jet is redirected into a different direction by a curved surface. Think of it as a curved pipe, and so it comes out of that experience going at a elevated direction relative to the original direction at 0.55 radians at an angle to the x-axis, and you're asked to find how much force is required to keep that plate. This is the plate that's, or the pipe that's that's deflecting the fluid. What's the force required to hold that in place? So the reason I think this is a good problem to do, or the reason I want to go over the solution in detail on this video, is I think it's a very good illustration of how important math is. So just really following the math, really understanding the math and following the math. It's not a hard problem. It's pretty much just a simple algebraic problem, but you have to really be careful with your mathematics and your problem setup in order to get the right answer. So the first thing is, this is a momentum problem. You know that because it is a force. They're asking you for a force, and so in our class, really the only equations that give us force that I can recall, are these two equations that relate force to velocities going in and out. We also have forces from pressure, so there's also pressure force, but that's not what's going on here. The fluid velocity is not changing, so there's not really significant, and the jet really can't sustain a pressure difference across it. So there's really nothing going on in an interesting way from a pressure perspective here, but there is a lot of velocity stuff going on. So we're going to look at this as a momentum conservation problem, and so to do that, we're going to have to define a control volume. And so the control volume that we're going to define is going to go across the inlet area there, and then of course it's going to come around, and then it's going to go back up here and do that. So that's my control volume. And the reason that's going to matter is because I really have to be careful with these guys. So these guys are going to be the normal vectors for the inlets and the outlets in the different directions, in the case, relative to different directions. In order to find those normal vectors, I need to know what the actual surfaces are through which the fluid is flowing, because this is a surface integral. So we're going to take this integral on the edges of the control volume that I've drawn, and in order to do that correctly, we need to know what that normal surface normal vector is. So it's important to have the control volume clearly in mind to do this problem. So, okay, looking at these two force equations, that's what I'm after, is force in x and force in y. Those are my two directions, x going to the right, y going up. This is the change in the control volume's velocity or momentum itself. So the change in the control volume itself is 0, because the control volume itself is not changing its velocity or momentum, or its momentum at all, because it's not moving. So the control volume is still, and so if you were to integrate that over the course of this whole box, it doesn't change in time. It's a steady state problem, and it's not moving. So these two terms both go to 0 because the problem, both the control volume is not moving and the problem is a steady state problem. So that's that. We're only worried about these guys. These guys are both surface integrals. They're integrals on the surface. They're only non-zero at a position where the velocity is non-zero at the surface. So this is a water jet. Anywhere that the jet isn't, there's just nothing happening, and I don't need to integrate that. So there's no reason to integrate here, no reason to integrate up here, because the water jet has 0 velocity up in there. No reason to integrate down here, over here. No water's passing through that. The only places the water's passing, it's going to have an inlet, in this region right here. It has an outlet in this region right here. Those are the two regions that have flow going through the control volume surface. So I'll call this the inlet, and this, of course, then will be the outlet. So I've got an inlet and an outlet that are at those two spots. And these integrals, they actually say integrate over the whole surface. And of course you have to, but these integrals are 0 everywhere except the inlet and the outlet. So you just don't need to worry about them anywhere except the inlet and the outlet. All right, so now we're going to set this up to integrate these two things over the integral of the inlet and the outlet. So for fx, on the inlet, I'm going to go ahead and put inlet here. And I've got u, so that's going to be my velocity at the inlet, and then rho, and then, u dot n hat, just like this. It's the same. I'm not actually going to change anything yet. I'm just going to say everything here is at the inlet. And then I'm going to have the same thing at the outlet. So I'm going to have two integrals, one of which is u at the inlet, and one of which is u at the outlet. Sorry, that's an n. These are all at the outlet. So that's that. So that's my first step. It's just recognize there are two integrals and they're different from each other. Now, I have u here and u here, but these u's are not going to be the same. The u at the inlet is going to be this 3 meters per second. So in order to see that, I'm going to make sure that everybody sees that. I'm going to write my real u. So my real u at the inlet, I've been told it's 3 meters per second. And which direction is it going? Well, at the inlet, it's only going the x direction. So my velocity is actually, is a 2D problem. So my u vector is 3 meters per second in the x direction and 0 meters per second in the y direction, right? Because there's no y velocity at the inlet. The y velocity of the fluid is traveling purely in the x direction. So I don't have any y velocity. So that's my u vector. And that's made up, of course, of u and v. So the two-dimensional vector is u and v. And this formula says I use u right here, that value. So I can do that. So I say, all right, fx is equal to, at the inlet, I have the value. It's 3 meters per second. I also know rho, so I'm going to put that in. Rho of water, 1,000 kilograms per meter cubed. No problem there. U dot n, I'm not ready to do that yet, so I'll just hold on to that. And I'll go over here and write inlet still. And then the outlet side, I have to figure out u again. All right, well, that's interesting. Now, my u at the outlet is not the same because now it's still 3 meters per second because I was told it has the same unchanged velocity. So the magnitude of u, I'll call it v here, I'll call it magnitude of u, is still equal to 3 meters per second. But it's not all going x. It's going in a different direction. So it's going 3 meters per second, but it's going 3 meters per second at an angle that is not equivalent to the x direction. Okay, so there's x and there's y. And so there's my 3 meters per second going in this angle theta, where theta is equal to 0.55 radians. So that allows me to calculate this in terms of a little u and a little v, right? Because u is going to be the x velocity, v is going to be the y velocity. So it's really easy to see that little u is equal to 3 meters per second times the cosine of theta, and little v is equal to 3 meters per second times the sine of theta. So that's simple. I plug that into my calculator. And your calculators do have sine and cosine functions. So that comes out to be 2.56 meters per second for the little u and 1.57, I'll use 3 sig figs, meters per second for the little v. So I'm just going to double check that here on my calculator. I got 3 times 0.55 cos is equal to, and I have it in degrees, so do it again. 3 times 0.55 cos. Equals, yep, that's right, 2.56, and 3 times 0.55 sine equals 1.57, right? So those are our outlet velocities. So now I can plug that into the outlet term here. So this is the outlet, and which one am I interested in? Well, back to the formula, follow it carefully. At this point, it's just the u component, it's just the u component of velocity, not the u vector, just u. And u for this one We just found it here. It's equal to 2.56. So I have 2.56 in that position. Then I have 1,000 kilograms per meter cubed, and then I have U dot N hat dA all at the outlet still. All right, so now I need the U dot N. So Fx, I'll move it over a little bit. Fx is equal to the integral over the inlet of 3,000 times U dot A. Well, why not? 3,000. This is now kilograms per second meters squared. But anyway, it's U dot N. So what is U dot N here? So U dot N, well, N hat for the inlet. So the inlet has an N dot. Remember, this is the shape of my control volume. Inlet is here. So the control volume out inlet surface normal points negatively. So it's so N for the inlet is equal to -1, 0, 0. So it's a unit normal, and it points in the negative direction because that's the inlet. At the outlet, it points in the positive x direction. So N for the outlet is equal to 1, 0, 0. All right, so the N for the inlet is -1, 0, 0 because it's on this left side. The pointing outward facing normal is going that way. And on the outlet side, it's pointing the other way. So those are my 2 unit normals. Now I just have to dot those with my U vectors. Well, my U inlet vector, we already said, oh, it's right up here. This was my inlet vector. It was 3, 0. So if you have N inlet U dot that, you have 3, 0 dotted with -1, 0. I'm only doing 2 dimensions, sorry. So don't do 0, 0, just do 0. It's not wrong to say 0, 0, 0. They just don't dot together if I only do 2 here. So anyway, that gives me -3. All right, so that's the answer. So it's -3 here, which you already knew because you've been using U squared. And that's D inlet, okay? But for the outlet, plus the outlet has 2,560 kilograms seconds meters squared times U dot N again. Well, U dot N this time is going to be positive 2.56 because positive 2, U is this. So that gives you 2.56 and 1.57. And I'm going to dot that with the outlet. So at the outlet, I have 2.56 and 1.57 dotted with 1, 0, 0. Okay, so that's 2.56. So you just get that 2.5. If you would not multiply by 1,000, you get 2.56 again. So 2.56 squared times 1,000. So that's what you guys have seen before. So that's what you're used to. But it's important to follow math here because this is not going to come out the same on the other one. So this one was -3 times 3. This one was 2.56 times 2.56, and then both times 1,000. And then the areas of the inlets and the outlets. So we'll pull all the constants out there. So on the left one, so we've got Fx, just to finish F before we get on to the more interesting Y. F is going to be 3,000, -9,000. And this is, of course, meters per second still. So we have -9,000 kilograms per meter second. Not kilograms per meters. Sorry, second squared meters. Times the inlet area. So it's not the inlet area yet. It's just dA inlet. But everything else is constant. So it's going to be the area of the inlet. That's what the math says. And then plus, we have 2.56 squared times 1,000. $6,554, and that's still kilograms. We decided it was second squared meters. And then that's going to be the outlet area, because it's going to be dA outlet integrated over the whole outlet area. All right, so I'm going to go ahead and try to find these areas now. The area of the inlet is pretty easy because we were told the diameter of the jet. The diameter of the jet is equal to 7 centimeters. So area inlet equals, I'll put down here, D jet equals 7 centimeters. So area to inlet is 0.035 squared pi. And so that's equal to 0.00385 meters squared. So that's my inlet area. So that's not hard. Hopefully you can, as I said, I'm just double checking. Looks good. So that's an easy area. It's just area of a circle. Area of the outlet, however, so Fx equals minus 9,000 kilograms second squared meters times 0.00385 meters squared. But the area of the outlet isn't the same thing. So this is where we're going to spend a little more time here. So why is the area of the outlet not the same? Well, the jet is the same. So the jet is still a cylindrical jet with the same diameter coming out now in this direction, where this is your theta equals 0.55 radians. And the velocity of the outlet is still the same, but that doesn't matter right now. The diameter of this jet, you were told in the problem statement, is still some d that's equal to 7 centimeters. That is, you're told the jet did not change its diameter as it came around the corner. So you'd say, well, why isn't the outlet area the same as the inlet area? The outlet area, the cross-sectional area of the jet is the same. Yeah, the cross-sectional area of the jet is the same, but it's not crossing in the same way. If you look at how this is going to cross this control volume cuts right across the jet. So the area here where it's crossing the boundary is in fact a circle. But that's not true up here. It's going to be, that's your control volume. You can see that when this crosses, it's not going to be a circle. It's going to be some kind of an oblong. So it's going to be, if you looked at it from the side, from the face on, it would be shaped not like a circle. It would be shaped like this. This width is still going to be D. It's not going to have changed, right? Because nothing's happening there. But if you look at the length of this oblong, it is going to be different. It's going to be longer and taller. So this is going to be a taller distance because it's at an angle. And if you think about this jet being even more exaggerated, like let's say it's almost shooting straight up. So here's my boundary, and if my jet is just barely angled, you can see that it could have a really long surface here, because the thing is, as you tilt closer and closer to being parallel with this boundary line, you're going to get a larger and larger area. So what is that? What is that? How do you correct for that? So it's going to be this oblong shape where the width, the length, the widths are all identical to what they would be for a circle that's crossing normally to the boundary layer. But all of these dimensions are increased in length. So that's the question: how much have they increased? So here's what it looks like when I just draw it as a triangle. This is my jet. So this is my cross-sectional area right here, my 7 centimeters. This is D equals 7 centimeters because that's the cross-section of the jet right there. But this right here is the hypotenuse of that triangle. So this is going to be longer than 7 centimeters, as we know, because that's what, we just said that. It could be really long here. So what is that? So, and what is this? Where is theta in all this? So theta is here, which means that this angle is going to go to, this angle of theta when this is 0, then this thing should also go to 0. So that's going to be this angle here. Like that angle, when this angle goes to 0, that angle goes to 0. And the thing goes back to being just a cross-sectionally, just like normal to the surface. So I'll draw it a little bigger. It's not great. Let me do it better so you guys can really see it. I'll make a really big picture. So here's my jet. It's got a uniform diameter. This is 7 centimeters. And it's crossing this boundary that is at this angle. So it's going to be bigger here. And so I want to draw this picture. So that's still 7, right? You can see that. It's the same as down here. But this is going to be different. It's going to be a lot bigger. And this right here is theta equals 0.55 radians. And that angle is the same as this angle, this one right here. And the way to see that is, we know it's got to be either this one or this one, honestly. But if this were to go to 0, then this whole thing would be just aimed right at the wall, and the theta here would also go to 0. Let's see, I'm trying to think if I can see another way to see that. Let's see, so it's also, if you look at this angle, kind of, if you imagine it keeps going, I'm trying to come up with a parallel lines way of doing it, but I'm not really seeing it right away. Anyway, this angle and this angle are the same. So that means that this 7 is the cosine of whatever this is. So I'm going to call this thing L. And you can see that from this picture that L times cosine theta equals 7. So L cosine theta gives you 7. That's what we know. So L is equal to 7 divided by cosine theta, which is equal to, clear, 7 divided by 0.55 cos. 0.55 cos is 0.853. So it's 7 divided by 0.853, which is equal to 1 over times 7. 440, no, it's not. 7 divided by 0.853. My calculator just tried to tell me that 7 divided by 0.853 was 41, but this is why, you don't just trust your calculator. You got to understand what might be happening here. Clearly that wouldn't be right, but 8.21 is believable. Anyway, that's true, but that's not, how do you find the area? So what you're going to do when you're finding the area of the circle is, well, you know the area of the circle when it's a uniform circle of 7, you know its area. If you elongate the circle like this, all of the widths, as I said, stay the same, but all the lengths are now going to get longer by this same 0.853 factor. So that means if you think of this as little slivers of area, each one of them is going to be longer than they would be for a circle by a factor of 1 over 0.853. So I'll just do the 1 over 0.853 here, actually. So that's 0.853, 1 over 1.17. So 1.17, I'll say 1.172. 1.172 is the increase in length of each one of these pieces of my area. So my total area for the outlet is equal to the area of the inlet, which is the circular area, times that 1.172. All right, so that's my outlet area, not the same as the inlet area. So my inlet area was 0.00385. So the outlet area equals 0.00385 times 1.172, which is 0.0045 meters squared. Meters squared. All right, so that's my new area. So they say it again. Think of it like each one of these little rectangles, it got longer as it went across this dimension, while the widths all stayed the same. So they all lengthen. So that's going to lengthen it in one dimension, not in the other dimension, and that's going to cause the increase to be the 1 over cosine increase in the area. So the area for the outlet is 0.0045 meters squared. So that allows me to go back to my X forces and actually calculate the force. So I had back here I was almost ready to be done. I had Fx was equal to whatever this was minus 9,000 times the area of the inlet, which is 0.00385 meters squared. And then I had 6,554. These units were kilograms per second squared meter. And then that times the area of the outlet, which I just said is 0.0045 meters squared. And I still have those kilograms second squared meters. So that's going to give me my X force. So my X force is minus 9,000 times 9,000 times 0.00385 is 3465 minus 34.65, and these are now newtons, plus 6,554 times 0.0045 is 29.5. Yeah, 29.49 newtons. So let's see what that is. I add those two things together. Negative plus 34.65 gives me, 5.16. Fx is negative 5.16. Now, a couple of people ask me, like, is this the force required is this the force exerted on the plate or the force required? This equation is a force balance, which keeps the control volume, because these are the forces that must be acting on the control volume. So you have your X force here, and it has to be that, the total force on this has to be that. So, this is the force exerted by the change in momentum as the fluids cross the boundary. So that's going to be give you the force, and so it is actually the force required to hold the plate. But the way you know this is not really by understanding that. I mean, that's fine. It is important to understand these are all the forces acting on it. So basically, there must be some force of negative 5.16 newtons in the X direction in order for this thing not to be moving, because my control volume is not moving. But the other way to understand it is just like, look, this jet's coming in, and it's hitting this plate, and it is deflecting, but it's still, which way are you going to have to push this plate in order to keep it from moving in the X direction? And you pretty clearly understand that if you shoot a jet of water at a plate, you're going to have to push it backwards to keep it from moving, right? This is our X direction. So, if you weren't sure, like, which it is, you're like, well, obviously, if you only did one of them, if you only had this one, if you only had water coming in and no water coming out, you would have to push it even harder. So that is clearly the force required to push on the plate to keep it from moving. So that's our X direction force right there. And we could then also do this in Y. So we're going to do it in Y now. And for Y, we had, where was my Fy equation here? Go back to my Fy equation so you can all see it. A while ago, apparently. There we go. There's my Fy equation. So we had this guy for Fy, and Fy right here. So we were doing the same thing, right? So we got the integral over the inlet of V times rho times U dot N dA in let, and then we've got the outlet. And it's V rho U dot N hat dA out. All right, so now I need V at the inlet. Well, V at the inlet is 0 because we said that the U at the inlet was 3 and 0. And V represents that Y velocity. So this is 0. So that whole inlet term is gone. There is no inlet velocity in the Y direction. So that's completely gone. That whole term is gone. So we only have one integral to do. We just have this integral to do. So we're going to say, all right, Fy is only equal to this one integral. It's the outlet integral. And the outlet integral does have a non-zero y velocity because this was the inlet, but the outlet u was equal to 2.56 meters per second and 1.57 meters per second. So it has non-zero x and y velocities. Of course, it's at an angle. We knew that. So that's my outlet velocity. Well, my little v is 1.57. So I get 1.57 meters per second there. Then, of course, I have the density, 1,000 kilograms per meter cubed. And here's the part that a lot of people made a mistake with. So then people want to say, well, it's 1.57 squared, but it's not, because that's not what u dot n is. So look at u dot n here. So this is u dot n, but we need a value for that. And then, of course, we're going to go do the a of the outlet. But u dot n is not 1.57. What is n? Well, n for the outlet, we already said it. It's 100 at the outlet. That's the unit normal of the outlet. And the u for the outlet is right here. So u dot n is equal to 2.56, 1.57, dotted with 10. Sorry, I keep adding that third one, I keep it being 3D here. But you do that, you don't get 1.57, you get 2.56. So u dot n is 2.56 meters per second, not 1.57, because the unit normal is in the x direction. So this is how much y momentum is being carried out of the box. So this u velocity is actually what's carrying it out. How much momentum is being carried out? Well, the amount of momentum being carried out depends on the y velocity, but the fact that it's being carried out depends on the u velocity. If there were no u velocity at that boundary, then none of the y momentum would be getting carried out because no fluid would be leaving the boundary at all. So, so we're at this boundary and you've got fluid leaving. The reason there's a y velocity, a y momentum change, is that there's upward velocity that's being carried out of the domain. If the velocity were purely upward, then the integral of this, of course, would be, there would be no fluid crossing the boundary, so there wouldn't be any change there. So there wouldn't be any flux across the surface. So the Fy is equal to 1.57 meters per second times 1,000 kilograms per meter cubed times 2.56 meters per second, all times the outlet area. We've already taken care of the outlet area. We know what that is. Same area as that. It's always the same as the other area, so it's the same outlet area. Area didn't change. But what changed is the velocity. So in this case, you've got 1.57, which is the v velocity, times 2.56, which is the u velocity, the x velocity times the y velocity, times that 1,000. So that gives you 4,019. And then you time the outlet area, which we said was 0.0045 meters squared. This is that weird unit again, kilograms meters squared seconds. So that gives you, or meters second squared, sorry. So that gives you the answer. So it's times 0.0045 meters squared, gives you 18 newtons. So Fy is 18 newtons. So in order to, so if you wanted the answer in proper form, here's the F vector. It's negative 5 point, I think we said 16, negative 5.16 newtons in the X vector, X direction, and 18 newtons in the Y direction. So that's my force vector required to hold the plate still. And that makes sense, as I said, because you got a plate coming in, it's getting deflected up. So in order to hold that plate still, you're going to need to exert a force that both pushes back and up, because the plate is going to be pushed down and over to the right by that incoming jet as it gets deflected. So that makes good physical sense to me. Final point to make is, is any of this force being supplied by pressure effects? So we have pressure crossing the boundary here on both surfaces. So you could say, maybe if the water were at high pressure here, then that would supply some of this F force, and so you wouldn't maybe need as much here, or maybe it's the opposite. Maybe this actually would push it even more that way. But there's pressure over here as well, and that's going to be pushing back the other way, and the areas aren't the same, but These are jets exposed to the open atmosphere here, P naught out here. So the gauge pressure in each of these jets is going to be just zero. They're going to be at atmospheric pressure because they're exposed to the atmosphere. And as we've discussed, jets can't really support pressure across their interfaces. They go to atmospheric pressure unless they're supersonic jets. This is definitely not a supersonic jet. So this jet is at P0 pressure. And because it's at P0 pressure, there will be no pressure contribution to the force either here or here. If there were a pressure contribution to the force, what that would do is change the number. It would not change these numbers. These would be the total force required to keep the control volume from moving. You would just have to take into account that some force is being supplied by pressure on that control volume. But in this particular case, the net pressure effect on the total control volume is zero because pressure is acting equally around the entire surface. So the net pressure effect is zero. So this is the amount of force you would have to supply to hold the plate specifically, negative 5.16 newtons and 18 newtons.